Good afternoon to all. I'm here to present some of the results we obtained in a project called CERIT, which was a project supported by European Space Agency in the framework of the Ocean Health Program. Of course, there is nothing strange in the magnetic wave of the Mediterranean Sea, but even if this magnetic wave started in May 2022, was the longest never observed in the Mediterranean Sea, and also because from another completely different point of view, we also would like to imagine that the dynamical system that produced the time series we observed was jumping between two equilibrium states or two attraction bases, if you prefer, related to the normal condition where we know it way and abnormal condition where it was expressed, in some sense paraphrasing the work of the story of Stevenson. Let's go to the next one. At this point, typically, okay, at this point, for tradition, there is people show the definition of magnetic wave given by Obday in his work of 2016, where essentially he defined magnetic wave like a significant deviation from a normal condition, which is defined from a statistic typically 90% percentile, or a deviation from what we imagine to be a normal condition. The problem at this point is not simply the fact that this is a quite arbitrary definition, but also that the question is what do we mean for normal condition? At this purpose, my attention was captured by this work that appeared on Nature Communication last year about the question of the need of a clear definition of magnetic wave, even if this was more focused on coastal region. But they captured the main question: what is normal? One answer can be given by the definition of the WMO, which said that even that we can consider a reference climatorial something which is an average of an interval of 30 years, with the last one ending by 0. Even this one quite arbitrary, but for the case of the satellite data, which means that only choice is 91 to 2020, and given also the fact that we are in a global warming scenario, okay, Sirius is not stationary, so there is the problem to, in some sense, to have a definition of mean in a by stationarizing the time series. Solutions are several. For instance, we can subtract trend using techniques like single aspect analysis, or other people suggested to have a moving reference center over the year of interest. And this given, as suggested by the other paper, to this, what they call dwelling definition, which define different approach to the average, and then will show different scenarios. Okay, to discuss better this problem, we use the Mediterranean Sea as a case study, and we published this paper this year, which was the result of the work we made during the project, where we analyzed the time series from the beginning in May 92 until the next April in 2023. The data are coming from the CMEMS, and this is a central figure of the paper. Here in blue, there is the climatology based on 91-2020 interval. In red, there is the actual measurement, daily measurement from satellite. This is another over the warm Mediterranean Sea, and in green there are the SST anomaly, and we clearly see the sudden increase of anomaly at the beginning, at the end of May. Here we start from normal situation, then we go immediately in few days with a 2 degree of anomaly in the warm Mediterranean Sea, which means that locally, especially in the northwest Mediterranean Sea, we had anomaly over 4 degrees for several weeks, and then we also had the winter anomaly in January, where you see the distribution of data with the histogram move over the positive value, and then we go back for interval before the new heat wave in April, where we had this bimodal distribution, which is a signal of the fact that the heat wave was present only in the western Mediterranean Sea and not in the east. Okay, if we want to put this event in the framework of a longer time series that started for the style data by the end of 1981, we got this Hoffmöller plot where x-axis at the time, y-axis the longitude. We made the latitudinal average of each longitude of the Mediterranean Sea from Gibraltar to Cyprus, and we clearly see the positive signal of 2003. Here you see the dotted line in the Hoffmöller plot evidencia data, and then the other signal in 2022. The difference between, if you zoom over these two periods, we can really appreciate the difference between the 2003 event, which was confined in the summer, while the event of 2022 started in May and is going on, especially the West Med, with an important event in January. Okay, this is another way to observe. Here, the plot was updated to April. This came in from CNCNR data reprocessed, which means the last data is 1 month before today. But the interesting thing is while the 2022, which is the green one line, was very strong, the 2003 was even stronger, reaching the higher value never seen in the Mediterranean Sea as average. But the very interesting is the 2024, where right now we are a couple of degrees higher than the average, and more than 2 degrees higher than the situation we had in the 80s. Going back to the concept of non-stationarity of the time series, this is in the upper plot there is the time series of temperature of annual mean, which show we are going linearly. We are linearly increasing from something like 19 degrees to nearly 21 degrees, with a slope of 0.4 Celsius degree every 10 years. And in yellow, there is the interval that typically we use for the WMO for the computation of the normal reference. The same applies for the season, with a stronger gradient in summer respect to the winter, which means that not only is increasing the temperature, but also the difference between summer and winter is increasing. Then we have to look at this. An alternative way respect to the percentile approach is to consider deviation of the average over a particular specific day over the 43 years in time. And if the distribution of the anomalies goes follow the Gaussian distribution, we can have a way to compute if the probability of a value with a confidence level higher than 90%. And effectively, if you look at the distribution anomaly globally in the Mediterranean Sea, we see that at least from a qualitative point of view, we have a nearly Gaussian distribution around the expected value. And this allows us to produce time series of anomalies. Here, there is the x-axis, there is the time, over the y-axis, time the standard deviation. So for instance, if you took a line along the 1.28, which means 10% over probability to be over this value. And if we plot the series at this level, we have the number of events that pass this threshold. If we define, we call the Marullo wave, if we define the Marullo wave, like if you use 99%, we have taken this one. If you develop this one over the time, this is the time series of percent of surface of the Mediterranean Sea, where an event was observed with this kind of confidence level, using the traditional method to subtract the average for the period 91 to 2020. And there is a clear increase of evidence, especially in 2002, where everything was going very close to 100% of the surface of the Mediterranean Sea, starting in April and never end until today, with some modulation due to events of strong wind, especially the west coming from northwest. If we want to have a look to the future, there were this work published this year by people of ENEA, where there is the forecast until 2100, we see that the heat wave continues to increase. This means that if we apply the updated criterion, 100% of the Mediterranean Sea will be under heat wave forever, every day of the year, especially in the last, these are several runs made with different scenarios from the more green one, we say, to the other one that we do whatever we like to do. Not too much to go in detail. So it's better if we go now in the no trend world. We use two approaches to the trend density. One was to use the single spectral analysis and remove just the first UF, which means the UF associated with stronger, with the longer period when you compute the eigenvalue of the correlation matrix, the spectrum or the eigenvalue. And another way is to subtract not only the first UF, but also all the UF that have a period longer than 1 year. What we obtain is a different picture, where now there is no an evident increase of the event, even if the important event like in 2003 and the events since 2022 are still present. If we do this is only leaving the first UF, which will be not so different from eliminating the linear trend. If we instead eliminated all the period longer than 1 year, that's via single spectral analysis, then this second picture will still the 2003 is present, and the events are more distributed. Just because I'm following the seasonal variation and the increase of seasonal variation with the trend. So we are shaded around the spectral value. Here is to better are the last 7 years. Just subtract the standard, the mean 91 to 2020, subtract the first UF, subtracting the first, the older UF with period longer than 1 year. And there is the difference between the first and other two. Even the two subtraction are quite, tell us the same story, essentially. Then last two slides are dedicated to the data we acquire in the Lampedusa station, which is in the central Mediterranean Sea between Sicily and Tunisia. Here is our mooring in the water with a lot of fish that you can meet in the evening at a restaurant if you want. And here is where the lab is located. Because we don't measure the buoy, not only the surface temperature, but all the meteorological parameters, including wind speed, heat fluxes, and CO2 flux interaction, and all the other things as I measure in the station here, which is very interesting because it's far from any contamination source. This is the series of data in the buoys from 2000 to 2017 when we started to work in 2024. We still show in purple, we see in purple the last year, which is similar to the average Mediterranean Sea. And then here, having a sense of temperature, not only 1 meter, but 2 meters, 5 meters, 18 meters, and 38 meters, we can appreciate the effect of the mixing due to the wind when the marine heatwave is stagnant, so measuring the penetration. And we see that typically, for example, this is where the blue line, which is the sensor at meter, is very different from the other sensor near the surface. And then there is a wind event. Everything is mixed until 80 meter, and when the wind stops, the stratification starts again. This means that the marine heatwave is just a few meters from the surface, and the wind, at least from this experiment, is the only way to that the heat penetrated to depth. I think that's all. I think I have no time to go through all the conclusion, but just the last one. There is also a student in the project to see the impact of the heatwave over the environment, and this is a paper which is actually under review. Thank you.
Thank you, Salvatore. That was a little bit scary. We have no time for questions right now, but we'll leave them for the discussion.
Anyway, I'm here.
Yes, thank you. We're going to continue with the next talk. This is going to be online by Christopher Marchand. from the National Center for Earth Observation and the University of Reading in the UK. Christopher, you were there online before. Did you mind turning on your camera so we can see you? And the talk is going to be exceptional global sea surface temperatures associated with the 2023-2024 El Niño. Thank you.
Hello, everyone. I never expected to be quoted in the Financial Times, which is the main business newspaper in the UK, but the events of last year in SST were so exceptional that they even made that newspaper. So let's have a look at the data. So this is the sort of plot we've seen a couple of times. The data here are from the ESA CCI, and the 1980s are in the grey lines. I've coloured 1991 in this plot in the red line. And in 1991, the sea surface temperatures, global sea surface temperature, averaged over -60 to 60 north, was warmer than any other year in the record. And just to show when we break a record, I've coloured the difference between the warmest and the next warmest years in blue so that they stand out. So let me play this movie. As we go through the years, you can see that the SST doesn't rise so smoothly. It tends to rise in steps, with a step whenever there's a big El Nino year. So we saw that with 1997, 1998. This is the long period of the so-called hiatus. And then another strong El Nino in 2015 and 16 pushed the global SST record up a bit more. And then there was the last El Nino. And quite strikingly, that last event not only was record-breaking, which we'd expect for an El Nino year, but was exceptionally record-breaking. This is why it was making the news. If we look at the data, the same data, in a more traditional way, the time series shown on the left, if we remove the climatology of the global SST around the annual cycle, from that we get the familiar anomaly plots. And in an anomaly time series like this, you can clearly see that El Niños have an impact on the global sea surface temperature, as well as there being a long-term trend and some other forms of variability. So what I'm going to do is decompose that anomaly time series in terms of 4 simple terms to see how much variability we can explain. The first term is El Nino. So using the El Nino 3.4 SST anomaly, I've fitted that variability to the time series. That's done asymmetrically between the positive phases and negative phases. So the positive phase can have a different global SST impact compared to the negative phase. That gives the lower line, the fit for that gives the lower line in the lower, sorry, the orange line in the lower plot. And then I've fitted a long-term linear trend, the effect of volcanic stratospheric aerosol with some smoothing and a lag term, and then also the smoothed solar cycle. That's the red line. And the data have all been fitted up to the end of 2015, which is where the vertical line is put, and then extrapolated using the same coefficients beyond 2016. And just those 4 simple terms explain quite a lot of the global mean SST variance over time. And that's shown in the top plot by the closeness of the orange line to the raw data. But you can see that after 2016, those 2 curves begin to diverge. The lower plot here is the residuals between the 2 curves in the upper plot. And if we fit straight lines to those residuals before and after 2016, of course, there's no trend in the period up to 2016 because we've already taken that out in the previous fit. But the only way to fit the data beyond 2016 is to add an additional trend. And that trend's quite steep. Since the previous El Nino, there was an additional warming trend on this fitting basis of 0.2 Kelvin per decade. That's the only way to fit those residuals. So the normal dependencies of the SST that had prevailed up until 2016 were supplemented by something else going on from 2016 onwards. Looking at this another way, we can look at the temperature budget of the two El Nino events, the last two El Nino events, so 2015-16 compared to 2023-24. I'm using an extended winter period from November through to March, and the El Nino effect peaks during that period. The difference in those temperatures as a global average again is 0.22 Kelvin. Let's see how that decomposes into the components that I presented. The continuation of the linear trend would have raised the temperature in that time period by 0.08 Kelvin. You might have noticed that the last El Nino event was not as strong as the 2015-16 event, and so the global effect of ENSO in this comparison is actually slightly negative. The solar cycle over radiance pushes the SST up. And one thing I wasn't able to get data for yet was the effect of the Hunga-Tonga-Hunga-Hapai eruption. So I've taken a literature value to represent that. So those are the effects that we could explain on the basis of the 3 decades of variability before the last ENSO cycle, and they add up to a warming of 0.09 Kelvin. So that's what we would have expected the record-breaking SSTs of last year to be. But they were much higher than that, as we saw. To put an uncertainty on this, I've considered the unfitted variance. Of course, those residuals have an unfitted variance, and the unfitted variance in a 5-month average amounts to plus or minus 0.06 Kelvin. And therefore, the extra that we need to explain for this year's event compared to the previous El Nino is the difference of 0.09 and 0.22, 0.13 Kelvin, with an uncertainty on that of 0.06. So it's statistically significant. And that corresponds to an underlying trend increase of 0.16 Kelvin per decade. So that's quite consistent with the previous way of calculating how much extra heating we had. They're both in the ballpark of 0.2 Kelvin over a decade. Now, does this mean that the long-term behavior of SST is showing an acceleration in its increase? Let's just roll back to think where that long-term linear trend in SST has come from in previous decades. It would correspond to the case where we have a relatively stable Earth energy imbalance over the long run. And that's not the radiative forcing, that's the Earth energy imbalance after the feedbacks on the forcing as well. But as well as that requirement, we get a linear SST trend if the distribution of that excess heat is stable across the climate system. So the same fraction of the EEI is going into the ocean mix layer. Under those two assumptions, we'd expect a long-term linear trend in SST over time without any acceleration or deceleration. So obviously an upward step in the EEI could accelerate SST above the multi-decadal linear trend. And in the past decade, greenhouse gas concentrations, particularly methane, have increased faster than they had before. And also, anthropogenic aerosols over the oceans have decreased from 2 effects, from the cleaning up of industry on land, particularly the eastern seaboards of Asia and the United States, and also because there has been a significant 85% cut in the amount of sulfur allowed in marine shipping fuel. And those are 2 significant sources of a decrease in anthropogenic aerosols over the oceans. So turning to look at the energy budget data we have available, that comes from series obtained from NASA. The raw data are shown on the left. There's a strong annual cycle in the Earth energy imbalance. So what we're looking at here is the net of the all sky top of atmosphere radiation, subtracting what's coming in from what's going out. So I've deseasonalized that, and that's shown on the right. You see the monthly data. I've also shown annual means using a year running from March to February, which gives us 24 full years. And then at the beginning of 2016, I've calculated the average EEI before that date and after that date so that we can compare the last El Nino cycle to what had happened before. And you can see that the Earth energy imbalance has shifted upwards by about 0.6 watts per square meter since 2016 compared to pre-2016. So is that all there is to it? Is that enough to explain, in principle, those SST changes? Well, the mean mixed layer depth of the ocean, to which the sea surface temperature is strongly coupled, of course, is about 63 meters. And if all that extra Earth energy imbalance were going into the mixed layer of the ocean, it could achieve a rate of 0.73 Kelvin per decade. So that's more than what we see. If we account for the relevant ocean area, you only need 25% of that extra EEI to accumulate in the mixed layer to deliver the recent record SSTs. That's one way of looking at it. If we look at it another way, we can do a calculation assuming a stable distribution. So the ratio of the mean Earth energy imbalance before and after 2016 is 1.7. And under the situations I explained, if the same fraction of that Earth energy imbalance is going into the mixed layer of the ocean, that's the same ratio for the SST trends. Now, the SST trend for the decades up to 2016 is 0.11 Kelvin per decade. And so using that assumption, the extra Earth energy imbalance would give us an additional 0.08 Kelvin per decade trend for the SST. Now, that is significant, but it's only half of the uptick that we have seen using the two calculations for the additional trend that we saw before. So half of that additional SST can be attributed directly to that EEI. So to bring this all together, the exceptional SSTs in the last El Nino phase can be budgeted as coming from 40%, it's the usual suspects, the long run trend, the ENSO, the solar activity and volcanic activity. 30% from this uptick in Earth energy imbalance since the last ENSO cycle, assuming that energy is stably distributed around the climate system. And then the rest is other factors. So let's draw a couple of conclusions from that. If this change in the Earth energy imbalance is to prove long-lasting, then we can expect that the new normal SST trend will be significantly higher than it has been up until recently, almost 0.2 Kelvin per decade. And obviously that would be a matter of very serious impacts. So we need to understand whether that's going to happen. And key questions there are, what's the nature of the other factors? Is it just some of the usual variability that we didn't fit? Or is it something more systematic and long-lasting? And what are the prospects for Earth energy imbalance? Was that uptick a blip or a persistent change? Possibly something to do with the change in anthropogenic aerosols. Lots of people are looking into that, but I haven't yet seen a consistent story on whether we expect those aerosol effects to affect the EEI in this way in the long run. So that's still an open question, and one that I'm sure this community will want to watch. Thank you.
Thank you, Christopher. We don't have really time for a question, but also there is a change in the agenda. For those that have been following online, you're more aware than me. We're going to have a coffee break now, and then we're going to come back, have the last talk, and then the discussion.